Hello, everyone. So in this particular video, I'm going to go over the proof of the spectral theorem. It is such a huge result in linear algebra that it really deserves an explanation. And also, it's such an amazing result in the end that a symmetric matrix can be orthogonally diagonalizable. It just has numerous neat applications. But it's really, really long. So because of that, if you wish to live in blissful ignorance, I completely understand if you want to just bag this. It is, after all, just one really long proof to explain the content. Although, that being said, it might be a good idea to stick with it anyway, just because as you guys go through mathematics, and you're going to take more math classes, you're going to be asked at some point, and very soon, actually, in the very next couple of classes here, you're going to be asked to prove things yourself. And the more experience you have to people doing it and being professional about it, you have a better chance in the future of knowing how to handle such a thing. So, and actually linear algebra is usually the first class that people start doing proofs in. It's just that I'm trying to avoid it because it's an online class and it'd be hard to actually grade things and talk about proofs. So let's go get started for those of you who wish to see the rest of the result. Now, there's two halves of this proof. I have to show that if the matrix is orthogonally diagonalizable, that the matrix is symmetric. I have to then show that if the matrix is symmetric, then it is orthogonally diagonalizable. The entire time, I'm assuming the matrix has only real entries. So let's do the easy one. We'll assume that the matrix is orthogonally diagonalizable. That means there is an orthogonal matrix Q, which is whose columns are just the eigenvectors, and a diagonal matrix D, whose entries on the main diagonal are just the eigenvalues, so that D is equal to Q transpose times A times Q. And remember, Q's inverse is Q transpose. So that means Q transpose times Q and Q times Q transpose. That's just the identity matrix. So now what I want you to do is just take that equation, D equals Q transpose times A times Q, and just multiply on the left by Q and on the right by Q transpose. Remember, if you have Q times Q transpose, that's an identity. And if you have Q times Q transpose, that's the identity also. So that therefore you get then that A has to equal Q times D times Q transpose. The minute we have that, all we have to do is take the transpose of that on both sides. I'm going to prove to you now that A transpose is A. So if you take A transpose, all you're going to do is take this equation and take its transpose all the way through. But if you take its transpose, you reverse the order of the products and you take the transpose of each term. So A transpose should be Q transpose transpose, D transpose, and then Q transpose. It's the original product written backwards, but then I take the transpose of each term. Now, Q transpose transpose by the property of transpose, this is Q, so that's why that's Q there. And D is a diagonal matrix, so its transpose is just the same thing, it's just D. And Q's transpose is just Q transpose. But that's what A is, right? That's Q times D times Q transpose, that's what A is. So we have, therefore, A transpose equals A. Therefore, A is symmetric, and we're done. That's one half of the proof, that's the easy one. Now, in the other direction, I'm going to now assume that we have a real symmetric matrix. I'm going to do this proof in a sort of an inductive manner. We're going to assume that the statement is true for all matrices that are size n-1 by n-1 or smaller. For any square matrix that is n-1 or n-1 smaller, that is real and symmetric, we're going to assume that it is orthogonally diagonalizable. From that, we'll prove that the statement's also true for a slightly larger matrix. So in a perfect world, if it's true for a small matrix, it's true for a slightly bigger matrix. But if it's true for that matrix, it's true for a slightly bigger matrix, and so on. And therefore, it's true for all n by n symmetric matrices. Okay, so here's the basic idea. First, we're going to bring to bear the ideas we've had about symmetric matrices and bases. So if asymmetric, that means it has to have real eigenvalues, and all the eigenvectors are also real. Since it has real eigenvalues. Let's just give me one. I don't care. Give me any one of them. For that one eigenvalue, there has to be an eigenvector. I also know that for an eigenvector that's within its eigenspace, I can then take any multiple of that eigenvector and still get an eigenvector for the same eigenvalue. So I'll not just get any eigenvector, I'll get one that has unit length. I'll call that x. Next, as an additional neat thing I showed you before, you can take any vector in Rn and you can extend it to a basis. Doing so is not very difficult at all. What you do is you think of it this way: you have a matrix A that spans a line, but then you can find a basis for the orthogonal complement. The line and the orthogonal complement together make a basis for the entire space. But when you do that process, you never actually change the first vector. So then when you extend this vector x to a basis for all of Rn, you still have x in the basis. But that vector, that set of vectors may not be orthogonal. So then, assuming the first vector is x, we'll use the Gram-Schmidt process to turn it into an orthogonal basis. In that process, remember the Gram-Schmidt process, the first vector doesn't change. So then that vector, x, is still in this orthogonal basis. The next thing is for each of those vectors, we can then change their lengths and not change the actual span of that space. So then I can take each of those orthogonal vectors and take a unit, I can divide by its length in order to normalize each of those vectors. That then results in a orthonormal basis. So actually this whole process that I just showed you, or just talked through for you, you can take any vector in Rn, and from it, if it's a unit vector, you can form an orthonormal basis from it. It's really neat. So then let's just call it x, comma, q2 up to qn. Now the vectors q1, q2 through qn, these are just vectors. They don't have to be eigenvectors. They're just vectors. But I do know that these vectors are an orthonormal basis. So if I form a matrix Q with these vectors as its column, that's an orthogonal matrix. So that's the matrix I'm going to use to begin the diagonalization process. Okay, so let's go do that. So let's consider the product. Let's take Q1 transpose times A times Q1. So then you have Q1 transpose, and I put vertical lines in order to emphasize the columns for you. That's transpose times A, and then you'd have A times Q1. But A times Q1, since Q1 is written in columns, you can just take A and multiply to each column of Q. So that product, A times Q1, that would then be this part right here. That is A times Q1. That's AX first column, AQ2 second column, up to AQN, the nth column. Good, so we now have that. But I know how to take a transpose of a matrix. So then if you take that first matrix, which is written in column form, so that would then be this guy right here. That's written in column form. If you take its transpose, all the columns become rows. And since the vectors are written in column form, by taking their transpose, they become row vectors. That's why the transpose of that first matrix becomes another matrix where I'm emphasizing the rows, and the rows are X transpose, Q2 transpose, down to QN transpose. But then in the second matrix, notice that A times X, X is an eigenvector, and we know it's eigenvalue. So A times X is lambda times X. The other columns, though, A times Q2, no idea, because Q2 does not need to be an eigenvector. It's just a vector. So I don't know what those will be at all. Now I'm going to do that multiplication. Notice that the way I've written the matrices, the first matrix is in row form. The second matrix is column form. So I can use row column multiplication. I'll write down the answer in this format like that. The only thing I care about actually is the first row and the first row and the first column. The rest of it we're going to call A prime. It's just some matrix. We completely don't care. We completely don't care what the hell it is. But focus on the first column. Notice that when you do the multiplication to get the first row, first column, you're multiplying this row by that column, That's why you get this. But X transpose times X, if X is represented as a column vector, that's a dot product. That's just X dotted with X. And we know X dotted with X is the length of the vector squared. But the length of X is 1. So the first entry, this whole thing right here, that just says lambda. It's just lambda. It's just that number. But then everything below it, you then have Q2 transpose times X. That's actually the dot product of Q2 with X. But we know that Q2 and X, that's part of that orthonormal basis. Those two vectors are orthogonal. So that means that this is a fancy way of saying 0. And in fact, all the ones below it, these are all 0. So the first column is lambda and then zeros. This mess here, no idea. It's just a bunch of numbers. And you know what? As you'll see in a minute, we don't care. It's just a bunch of numbers. We're just going to say it's a bunch of numbers. So the product looks like this. All right, good. Now I'm going to learn a few more things about this particular matrix. So if you look at that matrix, if you know A is symmetric, and you multiply A on the left by Q1 transpose and on the right by Q1, that's got to be symmetric. You can easily prove it the way I did before. Just literally take the transpose of Q1 transpose A times Q1 transpose. And when you take that transpose, you'll get the exact same thing back. Q1 transpose times A times Q1 transpose. We need to know that A is symmetric. So A transpose is A to do that. So this matrix here has to be symmetric. Well, the only way that could possibly be symmetric is that the first row is a mirror image of the first column. So all those stars, those are actually all zeros. Actually, every single one of them had to be 0. And we also can infer that A prime actually is also a symmetric matrix. So therefore, we now know that this matrix, Q1 transpose times A times Q1, has to actually look like this. And notice it's now been partially diagonalized. Partially diagonalized. But we also know that A prime must be real. It must be symmetric. And since A was n by n, A prime is n minus 1 by n minus 1. So it's a smaller size real symmetric matrix. So by my assumptions, that matrix A prime actually is orthogonally diagonalizable. So there is an orthogonal matrix U and a diagonal matrix D, so that U transpose times A times U transpose times A prime times U is equal to a diagonal matrix. I'm going to use that now to finish off the entire diagonalization process. To continue, I want you to form another matrix. We'll call this Q2. It's going to be a matrix written in block form. The first column is 1 and then zeros. The first row is 1 and then zeros. And then that other part of the matrix, which is an n by n, n minus 1 by n minus 1 matrix, that's going to be the matrix U. So it's actually the matrix U where you just tack on an extra row and column above it and to the left. That has to be an orthogonal matrix because U was an orthogonal matrix. So then Q2 has to be. Again, not difficult to prove. But then I want you to form the product of Q1 times Q2 transpose times A times Q1 Q2. Notice that if you take this transpose, you would get Q2 transpose times Q1 transpose. You could then focus in on the inner product like I did there. But Q1 transpose times A times Q1 is the matrix we formed before. It was that matrix where the first column was lambda and then zeros, and the first row was lambda and then zeros, and the other block matrix was A prime. But Q2 is 1 with zeros, and then 1 with zeros, and U in the right-hand corner. So then by writing down this multiplication in block form, you get what you see below. All you have to do now is to do that block multiplication. But if you do that block multiplication, you actually get that matrix. Everything, just do it like you always would. Just think about the letters like they're numbers, and you'll get this matrix. But that is the diagonal matrix. So that means then that if I take A and I multiply it on the right by Q1, Q2, and on the left by Q1, Q2 transpose, it's diagonalizable because I gave you a diagonal matrix in the end. But Q1 was orthogonal. Q2 is orthogonal. So their product then must be orthogonal. So that means then the matrix A can be orthogonally diagonalizable. It's quite long, isn't it? And it involves a lot of clever tricks using block multiplication. Is there a better way to do this proof? Yes, but not really. This is sort of the standard way to do it, even like grad school level. Like, this is essentially how it's done. You'll see the exact same proof in your book if you want to read it. And I believe that's enough for that video. Thank you if you actually sat through it all. Good job.